Hello, everyone. In this lecture, we will cover big idea number 2 from APCSP, which is all about data. In terms of dealing with data, computers, they work with numbers. And they have a special format, which is called the binary number system, which only contains zeros and ones. It could be really, really long strings of zero and ones. They are the only things that computers understand. We call each of them a bit. Each bit can be either one or zero. And we can also have larger units like bytes. Each byte is 8 bits. We're usually more familiar with decimal system when we use 10 numbers from 0 to 9 to represent each of the digits. When we need to represent a number that's more than 9, we go ahead and then use the next digit. So we represent it as 1, 0. That's the number right after 9. So in a binary system, instead of using digits from 0 to 9, we can only use two numbers or two digits, 0 to 1. So of course, that's a special way. We need to understand how to convert from decimal to binary and then binary to decimal. The whole idea behind the number system is called abstraction, where we want to remove all the details and make the problem to be more general. So let's take a look at some examples of how do we convert from decimal to binary and binary to decimal. First of all, we need to be familiar with powers of 2. And the basic principle to convert from decimal to binary is that we want to find out which powers of 2 adds up to the number. And then we're going to put 1 in that position. So I've listed some of those typical power of 2 that you should definitely be familiar with, like 2 to the 10th is 1024, 2 to the 6 is 64, and 2 to the 0 is 1. So now let's say we have a number which is 19. How do we convert this decimal number 19 to a binary number? So first of all, we need to find out the highest power of 2 that is less than 19. So if we look at this list of numbers, 16 is the largest number that's less than 19. So we put 16 here. And then the next number, if we add 8, that will be over 18. Add 4, that will also be over 18. So the next one we can add will be 2. And then finally will be 1. And 16 plus 2 plus 1 equals to 19. And then we can convert that into the exponential representation. So we have 2 to the 4th plus 2 to the 1 and 2 to the 0. So to convert this into binary, we have 1 at zeroth position, 1 at first position, and 1 at the fourth position. So these bits needs to be 1. And all the others that are not included in the calculation, they will be 0. Okay, so for the position wise, we start from the right to the left. This is the 0, 1, 2, 3, 4. That's how we count all of those binary values. Okay, similarly, you can do calculation for 58. So the largest power of 2 will be 32, and the next will be 16 because they add up to 48, right? So it's still less than 58. And then we can add up 8. 48 plus 8, that will be 56. And then plus 2, that will be 58. So converting that into the powers of 2, we have 5, 4, 3, 1. Those we need to have bits equals to 1. So 5, 4, 3, 1. And all the others will be 0. And we put a subscript 2 over here, means that it is a binary number. So you can go ahead and practice with some other examples to convert decimals to binaries. So this next slide shows how do we convert from binary to decimal. The idea is that we're going to sum each bit, multiply its power of 2. And remember, the rightmost bit is 2 to the 0. So like in this example, when we have this binary, okay, we have a 2 over here representing it's a binary number. So we have the zeroth position, 0 times that. The first position will be 1 times 2 to the 1, 0 times 2 to the 2, 1 times 2 to the 3, 1 times 2 to the 4, which is this bit, and then 1 times 2 to the 5th. Then we just add them up. This equals to 58. And that's how we convert binary to decimals. Binary numbers, not only they represent numbers, they can also represent many other things that the computer needs to understand. For example, like letters, A, B, C, D, we also have the corresponding binary codes for each of those letters. And then when we have strings, then it will be the combinations of those letters, right? Or it will just be a longer string of 0 and 1s. In computer science, ASCII binary codes, they are being used to represent each of the letter, like the big A in binary code, or in decimal code, in the ASCII code, it's 65, and it can be represented by this binary number if we do the same conversion as before. So that's letter. And then for machine instructions, for example, later on you're going to learn lots of instructions. Like this is just a very simple print instruction. We want to print out the string hello on the screen. There's a special way to encode this instruction into a binary string, which will be interpreted by the computers to understand, okay, this is a print instruction rather than some other instruction. And then the string of hello, like before, we can represent that using ASCII codes. Colors, they can also be represented by numbers. We usually call that the RGB value, representing the value for red, green, and blue. And with those different combinations of values, we can also generate many other values. For example, typically, if we have 255 for the value of red, 0 and 0 for green and blue, it's the red color. And similarly for green and blue. And then if we want orange, we want a lot of red, some of those green. By combining those, it will generate orange. And so for RGB values, we're using those three values where each value ranges from 0 to 255 to represent all those different choices of colors. You need to be aware of some of those common errors when we are handling data. One of the common errors is called overflow errors. Remember, we're using certain number of bits or bytes to represent each of those number. But when the number to be represented needs more bits than the programming language or the computer system allows, then that becomes overflow errors. For example, if in the computer system, integers, they can only be represented by 4 bytes, meaning 32 bits. What if we have a really large number that is already all 11111 all the way from the zeros to the 31st bit? What if I want to represent a number that's larger than this? Then we don't have enough bits, right? So it will generate an overflow error. And then another error could be rounding errors. It usually happens with decimal numbers. They could become really imprecise because we have to truncate some of those pointer values. For example, like let's say we want to buy 3 items, they are 10 cents each, and then we want to calculate the tax, say 7.5%. So the tax per item, if we do the calculation, will be 0.0075. Let's say in our point system, we cannot really represent that. So we have to round it to 0.01, just 1 cent. So that is a rounding type of errors. When we represent data, there are usually 2 kinds of data, analog versus digital. Analog is the type of data where everything is continuous. You have a continuous stream of data values. So you can see this particular figure here. This is like a sine function. For every continuous x value here, there's also a y value that can be represented. So between any 2 values, there's just infinite numbers in between. Digital data, on the other hand, will be just some fixed set of 0 and 1s that will approximate the analog data. So say, for example, if we want to approximate the sine function using the digital way, we're going to sample. So we're just going to sample, taking some samples at some defined intervals. right? Maybe it's an increment of 5 degrees and so on. And then only live the data with that intervals. Okay, so you can see the basic shape remains the same. It's just that we're not going to hold this many continuous data. So it's a conversion from analog to digital. This is called abstraction. Some other examples of analog versus digital could include, like, so for example, what I'm talking about here is continuous voice versus what is saved on the computer. It's digitized. I don't know whether you're still using this kind of thermometer, mercury-based thermometer, where the mercury, the height will change based upon your temperature versus a digitized thermometer. Metadata is an interesting idea. Metadata, they're not really the content of data, but rather they are the information about the data. We can usually use that to find the data in a more effective way. You can kind of consider this to be similar to the luggage tags, right? You put a tag on the luggage showing this luggage belongs to who and what is the address and so on. So similarly, metadata is showing some of those information. So for example, like in a PDF document, it has information like the title, what's the author, how many what are the keywords, and then when was this last modified or created, what is the size of the file. If you right click on a Word document, you can see all of those information. In the HTML file, there are also meta tag that includes keywords and what is the main content. When the search engine is looking for certain keywords and certain contents, they can just look at the metadata to get some idea. Nowadays, data have become larger and larger. Uh, for example, when you go buy a phone, right? Um, Before, we probably buy a phone with, say, 64 gigabyte. That's good enough. But nowadays, you probably need to use like 512 gigabytes because we take a lot of pictures and videos and so on. So files can become large quickly. And it is easy if we just want to store it because we just want to buy more storage. But however, when we try to send things from one end to another end, larger files can become problematic because, well, the network might not be that good. So compression is the type of technique that we can use to try to decrease the file size. So there are two types of compression. One is called lossless compression, which means no data is lost during the process while we try to reduce the size. Um, so of course, there's really not that much you can achieve if you don't want to lose any data. So the reduction is not going to be that ideal in this case. A typical example of this will be when you use the zip app, where it's going to, when you create a directory and then it's going to generate one zip of all of those files in that directory and try to make it to be smaller so you can send it over the network. How is Zip doing the compression is that it's looking at some of those repeated patterns that it can find in your text and so on. When they find those repeats, they try to use simpler pointer to represent it rather than representing this repeated text so many times in the text. A second type of compression is called lossy compression. In lossy compression, you're going to lose some data, and hopefully you won't see too much of a difference. The original cannot be restored from the compressed data, but the good thing about that is you can reduce the size more. If you can see these two images over here, one is PNG file, the other is JPEG file. Well, I don't know whether you can see that clearly. PNG files are usually of larger size, but you can see this image is much smoother than the JPEG one, where you can actually see some of those blocks. So when we are dealing with lots of data, there are many things that we can do in order to make sense of the data. Data can be collected from many different ways and from many different events, like orders we placed. These are called the raw data. So those data needs to be consistent so that we can use those data to identify patterns and to make sense of data. So how do we do that? Will be through those following steps. The very first step we do will be called cleaning. Cleaning means that we're going to remove some corrupt data or remove or repair some incomplete data and also verify the ranges. If you have data about age, then we need to remove those that are negative, right? Or those that are above 130 to make sure they fall within the correct range. Another example could be like birthday data. Usually, when we enter the birthday data, we make sure the months are between right 1 and 12, and then the dates are between 1 and 31. And for the year, we can make it to be consistent using 4 digits rather than 2 digits. So those are some of those cleaning job of the data. So after that step, those data can be more consistent. Your program will have some expectation of what kind of data you're dealing with. So the next thing is that we have so much data we don't necessarily need to use all of them. Maybe for certain problems, we just need to identify some subset of data based upon some condition. Like I'm interested in just the weekly rush hour reports. So I'm going to limit the data just to look at Monday to Friday and then only at those rush hours. And then don't look at all the other and then eliminate the data that I'm not interested in. So classifying meaning that we want to group data with some common features together. An example of this could be handling customer service data. When you have a customer service that receives all kinds of phone calls every day, you want to document those kind of data in terms of like which categories they belong to. So, for example, this could be a category that handles technical problem. Bias means that when the data we collected, they don't represent all the possibilities. For example, when I'm trying to build an app, a fitness app, where I aim to build the app for all adults, but I only focus on some data from younger active people. So the app will be designed in a more biased way because I'm not considering the whole spectrum of all adults. Sometimes it's interesting to find out if certain pattern emerges in a big set of data. So how do we do that is usually we try to have some hypothesis and then we process the data to find out if we can really draw that conclusion. For example, like for Amazon, they probably will be interested in like what products are frequently bought together so that they can have the recommender system. When you have something in your cart, they're going to recommend some other things that are usually bought together with this product. Correlation is one step further. It is trying to find out relationships between the data. But please be careful. Correlation only means those two things happen together, but they may not mean a causal relation. So relationships does not equal to causation. Like in this example. So in summer month, we often see higher ice cream revenues and also more pool rescues. So these two things are correlated with each other because it's summer. But high ice cream revenue does not cause more pool rescues and vice versa. So they are not causing each other. And when we are dealing with more and more data, scalability becomes an important issue. That means your processing time will not slow down with more data that you have to deal with. So cloud is a scalable way where we can have more people connecting to the cloud, distributed clouds over the internet, so that there's not going to be any single bottleneck where everybody needs to access. So a typical rule of thumb, let's say if you double the input size and then look at the runtime, if time more than doubles in this case, then you probably got some scalability issues. So we talked about all those different ways we can process the data. In reality, there are a lot of those tools in our daily life that can help us, like spreadsheets and database. They can help us to organize, and then we can filter, we can search, and then try to find out patterns among those data. So once the work is done, we process the data. It's the time to share those data with the company, with others. So when it comes to sharing, We will always say a picture worth 1,000 words. Use a lot of graphics when you try to share those data. Charts, tables, those are usually preferred. And so data visualization, that is a very useful way to showcase the result. So thank you. That's all about this lecture for data.